understand everything clearly, and just keep on asking question if you face any problem in between. So it is very much systematic approach to deal with probability. I told that here today's discussion is conditional PMF, not joint PMF. In last class we had already discussed about conditional joint PMF. Now we will discuss about conditional PMF, and it is very much implied from the concept that we had discussed in module 1, what we call it conditional probability. So whenever you try to calculate conditional probability mass function, then definitely it demands a better understanding of conditional probability, and we will do in the same approach in the few problems. So we will take few problems, and we will apply the same criteria how to compute conditional probability mass function. So today's outline, it contains only one part, that we will talk about conditional probability mass function, and using this conditional probability mass function we can calculate joint probability mass function. Again, if you ask how it is coming and to calculate joint probability mass function, then it is, I would like to say that it is just what generalization of multiplication rule, what we had already studied in module 1. So joint probability mass function is nothing, just it is talking about joint probability of two observed value of random, any two observed value of the random variable. So always if you, someone is saying that definitely it looks it is a definition of function, but always I translate that probability mass function in the form of probability. That means that probability always be denoted by capital letter. So what is the value of the probability mass function for this pair, order pair xy? So this probability, the value of the function for this order pair, it would be given by the, by definition, that probability that x is taking observing one value x, small x, and y is observing another value y. Okay, so that is the criteria, and many times I have already told that this comma, it is always talking about joint activity. So joint, we are trying to calculate probability of joint occurrence of one event x equal to x, another event x equal y equal to y, and I always used to say that this what it map back to sample space. So you can, with respect to this, you can define a event in the sample space, you can name it ax, and similarly with respect to this, you can define an event in sample space that we denote it by ay, and here I am talking about and is between these two. That means we are talking about joint occurrence of ax and ay, and hence if you are trying to calculate the joint probability, you can say that we are calculating the joint probability of ax and ay. And where is ax? Ax is in the sample space, that means it contains some outcome of the sample space, and ay also contains some outcome of the sample space. So we try to calculate probability of joint occurrence of ax and ay, that means intersection of ax and intersection of ay. And here what criteria we had taken till now? So x and y both happens to be a discrete random variable. So every discrete random variable, what does it do? It actually it define a partition of the sample space. So that's way usually we can get a very systematic form of ax, likewise also very systematic form of ay. If there is a common thing, then definitely this probability would be non-zero. It would be non-zero probability. That means PMF will take a non-zero value, some probabilistic value we will get for here. So it is all about calculating joint probability mass function. Now today we will discuss about conditional. So conditional, again I will relate it back to conditional probability, how it will come. So here in last class I had already given the definition. I am again recalling it. So why we are going to study about conditional probability mass function? So what is happening in many situations, we actually we are having just partial information about some random variable, okay, or about some outcome which is coming from the random experiment. Okay, we are having just partial information. So based on that information, we try we try to come up with the probability of the associated random variable or probability distribution of the observed value of the random variable. So that's why we need to introduce conditional probability. So we are interested in how this information, that partial information, changes the probability of event involving random variable. So how this once we are having partial information, whether that information is going to change the probability of the observed value of random variable or not. So that scenario will take. So the conditional probability mass function address such scenario. That means here we are having random variable x. If you don't observe any partial information, then just we try to find the probability mass function of this. How? Just by calculating simple marginal probability mass function. So this was the approach, but somehow we came to know some partial information. Suppose name this partial information a. Okay, so now we are having a new random variable that we will call it x given a. So this random variable will have a new probability mass function that we will denote it by conditional probability mass function. That means this p would be, whenever I am saying that probability mass function, in that case that p always happens to be a small letter, because it is a function, a general notation, and we have to be specific. So here we are introducing conditional probability mass function. Some book refer here x given, in the argument also they refer it to here a, but we know that a is already, you have already observed, so you can excuse here a in this notation, you can excuse but for better understanding you have to proceed with a, because you ultimately you have to apply conditional definition of conditional probability mass function. You can proceed with here variable thing is only x, the value that x is or observing once you have already having a partial information, okay, or something. So that we will define it here like this way. So consider x be a discrete random variable with probability mass function p of x. So that means we are having probability mass function of this one. Okay, once p of x. Okay, but we are not this probability mass function. Likewise, in conditional probability approach, this probability mass function you can say that it is your prior probability mass function. Simply, you can say that. But what is happening? You are observing one event A. Okay, so based on that, if your things, you are some, definitely there would be some kind of update due to that observation, observation of the event a. So that's why you are getting a new probability mass function that we will call it conditional probability mass function. Okay, and remember that the happening of a, it must be what must be in positive probability. That means definitely some outcome of a, in a must contain some outcome. That means it is not like that a would be a null set kind of null event kind of thing. It is not like that. That means a definitely contains some kind of information. It is not like that there is no information. So in that case, it would be meaningful to proceed with that partial information. So that's why we are taking condition that probability of a is greater than 0. That means there is some meaningful outcome there in a due to happening that observation of a. Okay, then conditional probability mass function of x, we can define it like this way, that probability mass function of x given a, it is defined as the this probability, that p probability that x is observing value x given a. So more importantly, I had already told that if you are talking about x, one random variable is taking a value, observing a value x, then always we can term it as event. Why? Because it will map back to some kind of uh, pre-image in the sample space, and that means collection of some outcome. That means we are saying that ax pre-image of this one, it is collection of all the outcome from the sample space which has been mapped to the observed value x. So that is the scenario. That's way either definitely it is out event happens to be collection of some outcomes. So likewise, we can say that this value observation also, we say that it is outcome. So we used to say that it is outcome. So it is all about what we are. Once you convert this function as a in term of probability, so it is all about conditional probability. So we are finding the conditional probability of event x equal to x is taking value, observing value x, that we can reverse back, map back to ax given a is the observed value. Okay, so how we can calculate this probability? So just we have to apply the definition of conditional probability. What does it say that always I would like to say that how much of this event is happening within a, so that we are talking about joint occurrence of the event x is observing value x with a, so joint occurrence of this event and this event, so divide by how many outcomes of a is happening, total outcome of a is happening, so that we are calling it probability of a. So this is what, this is the definition of probability, conditional probability. Directly it is coming, that means how much of x equal to x is happening within a divided by uh, how many times a is happening, so that what is the chance of happening of a. Otherwise also you can say that. So this is just what we call it, it is conditional, directly coming as a conditional probability. Now tell me, so further if you try to express this, if you try to relate this conditional probability, this is the conditional probability mass function, and if you try to relate it with prior probability mass function p of x, how you can denote it? Anyone can give idea? Just use the bifurcation rule it here. So two situation it may be here. What this observed value x, either it might be in this partial information a, or it might not be in the partial information a. So two scenarios, that means binary scenario will come. Either it would be in the a, this x would be in the, it would contain a, that means the partial information a, it is containing a, or it is not containing a. This x is not in a. So two information, two scenario we may have. So if x is within a, so in that case this joint occurrence of x equal to x and a, it just becomes x equal to a. X is, that x is observing a, and we know that x is also in a. So in that case this one would be what, it would be just unconditional probability mass function of x. So simply this will translate into like this way, probability mass function of x, because x is already within a in that scenario, I divide by probability of a, divided by probability of a. Now we are going for second scenario when x is not in a. In that case there is no common thing between this event and this event. That means the intersection is empty, null set. So what is the probability of that? In that case 0. So 0 by probability of a always happens to be 0. And why? Because probability of a we have taken a positive number. So that's why when x is not within a, then definitely we will say that the condition value of conditional probability mass function will take 0. If x is within a, then this pro, conditional probability mass function will take this value. That means the marginal probability mass function of x divided by probability of a. So this is the definition of conditional probability mass function of x given a. A is the partial information. So we will visualize it here. I will give again a visualization picture. So to obtain the conditional probability mass function, we add the probability of the all the outcome that give rise to the observed value small x, and jointly those observed value are also in a, and then we normalize it by probability of a, because definitely if you are calculating probability in that way, then some will go higher than 1. So we need to normalize it, we have to bring it back to what the criteria of being a probability mass function. So scenario is coming like this way. So you can see like this way. If you are taking one observed value x, okay, so one observed value x, you observe how much intersection it is happening, it is happening within here. And if you take x dash, the how much intersection it is having with a, this much intersection. So in order to calculate the probability of x equal to x given a, so you always what it will it is having very small intersection, relatively smaller than this one, so that's why this that corresponding probability is smaller, and this one is bigger. So always you will see that in the definition you had already seen that the conditional probability mass function is directly proportional to what we call it that prior probability or marginal probability. So this one was how it was defined as. It was defined as, so I'm just leaving given a, you can add it, there is no issue. So it was defined as marginal probability of probability mass function of x divided by a when x is within a. We are just worrying about only those x which are within a. If that x is not contained in the given information, then definitely the corresponding conditional probability mass function would be 0. In that case, if x is not a, it is 0. So easily you can say that this conditional probability mass function is directly proportional to the what we call it marginal probability mass function. So easily you can say that if x is covering this much area, definitely that will have higher probability mass function because it is having a bigger area, and intersection is also bigger. So that's why this probability, this bar is bigger and this one is the smaller. So this is the visualization of conditional probability mass function where condition is condition on a. So here we will take one example, then we will take few more examples. Suppose this clock problem is very interesting kind of problem. So the minute hand, so in clock if you observe there are three hands, one is minute hand, another one is hour, and third one is what second we used to call it. So three type of hand happens to be there in clock. Okay, so the minute hand in a clock is spun, and the outcome omega is the minute where the hand comes to rest. So that scenario is very much clear to everyone. So that wherever that minute hand will stop, that will say that it is of that measure of minute. So if it is stopping at one, then then we will say 5 minutes. And then if it is stopping at 2 hours, that it is saying that actually our measure happens to be in bold, and minute actually those are ticking, just ticking, and those happens to be very small. So easily we are very much aware of those, that clock. Just take consideration of what wall clock. Okay, so because that would be of bigger size, and there you can visualize all those activities of three types of hands. Okay, so here our sample space, it includes that measuring the activity of minute hand. Okay, and outcome here omega, it is talking about the minute where the hand stops. So what are the possible value omega will take? Anyone? What are the possible value, and what would be the corresponding probability mass function, or simply distribution? Anyone would like to say that? Am I audible? Okay, I'm asking that what kind of value omega will take? What is the outcome? Just try to identify outcome. What is outcome here? No response. If you try to go outcome wise, each outcome is dealing with a stopping of minute hand at particular place. So that's way the omega will take either 1 2 3 4 5, it will take up to 60, it will go up to 60. And what equally likely situation is here. So if omega that minute will stop at 1 minute with 1 by 60 probability, it will stop at 2 with 1 by 60 probability, likewise it will stop at 60 with 1 by 60 probability. So in one clock, in one round, how many stopping that minute hand will have? Definitely 60 a stop it will have. So that's where this is the possible sample space, you can see that. Now here we introduce a random variable. Let x be the hour where the hand comes to rest. So this is the random variable here in this we are introducing. So here question is that we have to find the probability mass function of x first. Next we have to find the conditional probability mass function of x given two scenario. One scenario is first scenario, that first information it is talking about first 4 hour. That means first 4 hour means 1 hour, 2 hour, 3 hour. Okay, first 4 hour. A second scenario or partial information given here that here that omega is talking about minute. It is as a outcome. So when your outcome, that omega is between 0 to 11, between 0 to here, exclusion of 0 and inclusion of 1. Okay, so if you try to convert this one in hour basis, so what would be possibility? It would be what between 0 to 5, it is talking about 1 hour happening of x, that one. And if you talk about 5 onward to 10, 5 onward to 10 minutes, it will talk about second hour in the clock. Just draw a clock. So this is the not, it is a perfect way. So here this one is 12, it is counted 12 or 0, or 0 you can call it like this way. This one is 1, this one is 2, this one is 3. So if I am talking about 11 minutes, so 11 minute it will happen here. This would be 11 minutes. So we are talking like this way. So in that case, so we have to find the conditional probability mass function of x. And what are the possible value x will take? It is talking about the hour where a hand comes to rest. So x will take value either 1 or 2 or 3 or 4 up to 12. There are 12 hours. Okay, 12 hour, 12 okay, that is the situation. So uh, so it is already given here, you can see it like this way. As I told that here, the hand is equally likely to rest at any of the minutes. So that's why the sample space would contain 60 outcomes. Okay, and each outcome is having probability 1 by 60 due to this equally likely situation for anything. So it is all about the story about outcome. Okay, now we try to focus on x. X is talking about stopping our hand which stop at 12 place. So x will take what are the value 1 2 3 up to 12. And if you are calling what are the probability for each value of x, and again we will say that hour is also distributed equally likely fashion. So that's why the x will have probability mass function 1 by 12. Very easy to find the solution of this one, probability mass function of 1. So one we got it, answer for this one we got. Now second question is coming that we have to find the conditional probability mass function. So conditioning is happening through this way and this way, these two. So how we can find it? Anyone? Just apply the definition. What is A? Anyone just try to respond it. Definitely, I would answer it. It is not like that. I will leave it as homework. Uh, Tell me, just try to answer it. I told that idea is just hidden there in the definition of conditional probability. So once you are going to calculate conditional probability mass function, just apply the definition, and that definition has been borrowed from conditional probability definition of conditional probability. So just calculate the here conditional probability mass function. That means calculate here. conditioning first introduced by this partial information a is talking about first 4 hour. So what are those first 4 hour? 1 hour, 2 hour, 3 hour, 4 hour. So a is like this way, hourly division like this way. Now tell me what would be conditional probability mass function for the given a? Anyone would like to calculate? So here, what are the possible value of x? If you don't know anything, just take all those possible value and calculate this conditional probability mass function. Whether I am audible or not, I am not getting a response from any one of you. Venkat, are you listening me? Very fine. Any other one would like to respond it? Hasita, how we define that? How we calculate that conditional probability mass function? If you are listening me, then just try to answer it. Ashish, any other who would like to answer it? Okay, fine. I need to answer it again. So how you can find calculate the probability of this conditional probability mass function? So I will treat as uh, the definition says that it is talking about that probability x is taking value or observing value small x given a. A is what? Talking about first 4 hour. So we x will take x is taking how many value? 12 value. So for each value we will try to calculate it. Okay, whether we see common thing between the observed value of x and a or not. So if we are taking x equal to 1, then 1 definitely it belongs to a. And how many value a is observing? 4. So and equally likely assumption is given here. So that's way if you are taking x equal to, if someone is going to calculate conditional probability mass function for x equal to 1, then that would be from the definition of conditional probability mass function, it would be what? 1 by 4. Why? Because probability of a is what? Probability of a is, if you try to calculate, it would be try to calculate 1 by each one is having probability 1 by 12. You can see it here. So 1 by 12 plus 1 by 12 plus 1 by 12, you have to add it 4 times 4 by 12, and probability of x equal to 1. If you try to look it from here, 1 by 12. So 1 by 12 divided by 4 by 12, and if you simplify it from the definition of conditional probability, it would be 1 by 4. Likewise, if you take x equal to 2, 2 is also in a. So what is the probability of 2? X equal to 2, that would be also 1 by 12, and probability of a, we know that it is 4 by 12, and hence we can say that probability, conditional probability mass function for x equal to 2, it would take again 1 by 12, 1 by 4. And likewise, for if you take 3, 3 is also in a, 4 is also in a. If you take 5, 5 is not in a. So for that case, probability mass function for x, conditional probability mass function for 5 here given a, it would be what? 0, because we don't observe 5 in a. That means there is no common occurrence of 5 and 8 together. So that's why null set kind of a thing is happening. So probability this would be 0, and conditional probability for 6 would be also 0, 7 would be 0, for 8 also it would be 0, 9 is so it would be 0, and for 12 also it would be 0. So that's way, if you try to talk about conditional probability mass function for given A, it would be 1 by 4 when we are taking value x is taking value 1, 2, 3, 4, otherwise it is taking 0. And you can easily see that this conditional probability mass function, it is a legitimate probability mass function. Why? Because it is satisfying all those three criteria of being probability mass function. First, positivity, that means greater than equal to 0. Second, normalization condition, if you sum the value of probability mass function for each value of x given A, then it will sum to 1. Why? Because 4 times 1 by 4 it would be equal to 1. Now we will try to calculate another probability mass function, that conditional probability mass function, due to this second partial information B. So we introduce conditioning over this one. So when, so again x will take all 12 possible. Now do we see any common thing between this value of x and B? When we will see common thing, so x is talking about here, remember that B, it is defined in term of hourly basis. So if you try to, B is defined in term of, sorry, minute basis. So if you want to convert in term of hourly basis, so you have to convert like this one. This one is equivalent to, say that initially I had already told that, so it will talk about 1 hour, 2 hour kind of things will come, and up to 3 also you can take it like this way. There would be some common things. So because 11 is coming, so 11 minute is happening between, just after 2 hour, just after 2 hour 11 minute will come. So that's where 3 will also come with little information. Okay, so we try to calculate here things like this way. Suppose x is taking value 1, that means whether that one is, this one is talking about hour, this so 1, x is taking value 1, so 1 does include whether this occurrence of 1 is dealing with A, there is a common thing between 1 and A, definitely there is a common thing. So 1 is x equal to 1, so 1, this is the one, this is the one. Okay, x equal to 1, and how many outcome is happening, how many times B is happening here in that perspective. So common things, we will observe that 4 times it is happening. And if I simply if I 4 times, and how many times B is happening in total, it is talking about minute. So minute, we are not including zero minute, we are including excluding 0 here. So that's why minute, it will talk about 1 minute, 2 minute, and likewise it will go up to 11 minute. So up to first hour, how many times the minute hand will stop? 4 times, we are not including 0, so 4 times. So this one, 1 time, 2 time, 3 time, and at exactly 1, 4 times, 4. So that's why how many times that x is happening in combination with B, 4 times. So probability would be 4 by 10. Likewise, conditional probability for x given B, for x equal to 2 it would be 5 by 10, and likewise for x equal to 3 given B, it would be 1 by 10, only one time, this only this one is happening. So that's why 1 by 10. Okay, so 1 by 10, and for other value of x, the conditional probability mass function would be 0. So only these are the non-zero value of probability mass function: 4 by 10, 5 by 10, 1 by 10. If you sum it up, it is also satisfying normalizing condition, that means sum will add up to 1, and for rest of value of x, it would take 0 value probability. So very again, it is a legitimate, this conditional probability mass function is a legitimate probability mass function. This kind of question will come there in your quizzes and exams, other exams as well. So be attentive. Now we will take another example. So before going to that example, I will talk about one particular scenario to calculate conditional probability mass function. Generally, I told that here we are dealing with a discrete random variable. So in order to deal with discrete random variable, what is happening, that always x is taking value in discrete fashion. So we can talk about discretization of the value of x, or uh, like sequencing the value of x we can put in a particular sequence. So let x be a discrete random variable with protein mass function. Definitely there would be protein mass function, given protein mass function like this way, and a be an event defined in term of like this way. It would be saying that x is taking value 10 onward, or after greater than 10, or x is taking value some discrete value. Definitely it would be discrete between any two integers or numbers, or that kind of situation is coming. And for then what is happening, then how we can define conditional protein mass function for x, xk, that kth member of the range of x, because why, the x is a discrete random variable, so that's why the this range of discrete random variable, it can be written as a single sequence like xk. Xk we have taken due to discrete nature of random variable. Then in this scenario, what is the definition of conditional protein mass function? That x given a, it would take simple this we call it definition of the conditional probability mass function, and further just apply the definition of conditional probability. It will take this form, or finally it will be translated into this in this form, which involve the prior or marginal probability mass function. Here when x is within a, then simply we observe definition of conditional probability mass function as a ratio of marginal probability mass function divided by probability of a. And if we suppose xk is not in a, in the given information, then what would be the value of conditional probability mass function? That would be 0. Now here we introduce a random variable x like this way. We are taking this is the second question. Let x be the time required to transmit a message, okay, and we assume that the x is uniformly distributed. That means each value of x is taking uniform probability. It depends upon how many value x is taking. So suppose here range of the x is given, that it is that time taken is from 1 to L unit, some unit, whether you can call it minute, hour, or whatever, depends upon your situation. If nothing is mentioned there, by default you can take unit from your perspective, second or something like. Okay, so if I'm talking about what is the protein mass function of this one, then very simple. Here it is x is distributed uniformly, so protein mass function of x would be what, it would be 1 by L for each value of x. So x is taking for each value of x. So x is taking what are the value? 1, 2, 3 up to L. So this is the protein mass function of x. It is already given here. Now our question would be here, we have to find conditional protein mass function based on some conditioning. So conditioning is coming like this way. Suppose that a message has already been transmitted for m time units, then we have to find the probability of remaining transmission time, that is what, j unit. That means up to m unit we have already observed, starting from 1 to m, a message has been transmitted, and we have to look for m plus 1 onward to L. So we have to find the probability that the remaining transmission time is j times unit, and how we can find that conditional probabilities. Conditioning is observing. So what is the, so if this event, if you translate in term of this information, if you translate in term of events, then it is saying that x is taking value here greater than m. A message has already been transmitted for m times, unit. Okay, that means definitely for m times unit, that means value that x will take value what, greater than m. And here now we have to look on our observation of x. It is what we have to observe for what scenario, we have to observe for m plus j, such that this quantity would be greater than uh, afterward of m, that means m plus 1, it will go up to j. So we have to find the conditional probability mass function of x given a, x given a, So here x is taking, so what are the possible value x will take? It will take m plus 1, m plus 2, m plus 3, likewise it will go up to L. So how many possible value x will take? So L minus m, simply you can subtract it like this way, L minus so L minus m. Okay, so those value, those kind of value will come. So if you try to calculate this conditional probability mass function, again we will take this definition of conditional probability mass function, that means joint occurrence of x equal to j with a divided by the total occurrence of a, how much times a is occurring with what probability, occurrence of the chance of occurrence of a. Okay, so we know that if suppose we will take only this scenario when j is within a, there is a common thing between this event and this event. So if you suppose j is within a, that means j is greater than m, in that case definitely what is the distribution of a, that prior distribution or marginal distribution, that one is uniform 1 by l. So 1 by l divided by how many times a is happening greater than m, how many time you observe, L minus m. So L minus m divided by L will come. If you simplify, the answer would be 1 by L minus m. This is the conditional probability mass function for this event. Now further we will talk about from general perspective. So here we observe condition with respect to one event. Now we will see the condition with respect to random variable. With respect to random variable, when you are saying one event, that means you are talking about fixed number of observed value of a random variable. Now we will go to generalize it further, that means we are having two random variable x and y. Now we will talk about conditioning, we will conditioning over one random variable y, and due to that what kind of probability mass function x will have. So if you put conditioning over y, that means we are observing few value of y, or all value or few value of y, then what kind of changes we will observe in the probability mass function of x, that things we will discuss it here. So how we define it like this way. So conditioning, we are putting over second random variable y. So conditional probability mass function of x condition on y, it would be defined again the similar fashion, that probability that x is observing value x, and given that y that we have already observed, that y we have already observed. So how we define it? So this will be converted into this conditional probability. So this is the definition of conditional probability mass function for x given y, and it is defined like this probability, and this probability is now it is further defined like this conditional probability. So it is talking about so you can simply see the difference between notation, both are same, but here notation is different, here notation is different. So we are converting further this one as a conditional probability. So this is what it is, total conditional probability. It is in term of conditional probability, that means one event is this one, another event is this one. So this conditional probability, how we define it? We define it as a ratio of joint occurrence of this event and this event, that means how much time this event is happening within this event divided by total occurrence of this event. So total occurrence of this event, so it is happening how total occurrence, that means what is the probability of occurrence of this event. So like this way. So if you further zoom it out, what does it talk about? So it is talking about joint probability of x and y. So this one is the definition of joint probability of x and y divided by what is this? This one is the marginal probability of y. So conditional probability of x given y, you can talk about it is a ratio of joint probability of x and y divided by marginal probability of x and y. So this is the this is very interesting kind of relation. You can observe that relation between joint probability and conditional probability. From here also you can derive it. If you try to take it left hand side, then what you will observe? You will observe that your conditional probability mass function is what can define joint probability mass function. How it is defined like this way. So suppose we are introducing conditioning over a, that means first we observing sorry, we are introducing conditioning over y, that means first we observe value of y. So that's where marginal probability mass function of y will come first, then we need to multiply it with conditional probability mass function of x. Conditional probability mass function of x given y. This is, so what is this? This one is, again, it is a generalization of multiplication rule. So if you are willing to calculate joint probability mass function, first introduce conditioning over any of the random variable x and y, whether you go for y or you go for x, depends. So that will define the order. Okay, and based on that, you secondly you have to calculate conditional probability mass function and multiply these two, you will get your joint probability mass function. So that, so you can say that the definition of conditional probability mass function leads to calculate or computation process of joint probability mass function. So here you can say that the conditional probability mass function as a function of x has the same shape as this one, the joint probability mass function. Why? Because for this we are calculating for each x. So for each x, this means for each, we are calculating for each y. That y is second random variable y is observing. That means we are fixing y. So we are observing y. That means we are fixing. That's why at that moment when you fix y, this quantity in denominator it would be fixed, and hence we can say that here x is only variable in nature. So whatever shape this one would is, it would be directly proportional to this joint probability mass function. So shape and all the characterization of this conditional probability mass function, it can be borrowed from the characterization of joint probability mass function. Okay, and what we for, and to further characterization, in order to make it a proper legitimate probability mass function, we have to normalize it by this marginal probability mass function of y. That one is the process that it directly came from the definition of conditional probability mass function.